In this video, I am going to discuss the Huntington-Hill method of apportionment. This is similar and different to the three different divisor methods that we talked about in the last section. So just to recap, an apportionment problem is a fair division problem where players are entitled to a differing percentage of a set of goods but must receive a whole number of items. And all of the items are identical and indivisible. And as always, our traditional problem here is determining the number of seats in the House of Representatives that a state will receive. The standard quota is the number of seats that a state will receive in the apportionment, and the problem occurs when the standard quotas are not whole numbers. Since a state cannot receive a fractional seat, we have to figure out how to handle this. So the Huntington-Hill method was introduced in the 1920s and is actually what we use currently. It was developed by Joseph Hill and Edward Huntington, two men who worked together on this technique. Now, the Huntington-Hill's method uses something that is called the geometric mean. And this is not a thing that a lot of people learn about, so I'm going to teach you about that quickly. It's not that difficult. So the geometric mean of two numbers, which I've called x and y, is computed by taking the product of the two numbers and then finding the square root of the result. And it looks like this. So in other words, you just multiply the two numbers together and then take the square root. So you will definitely need a calculator in order to complete this apportionment. So just a quick example here. If I want to find the geometric mean of the numbers 20 and 30, first thing I do is I multiply 20 and 30 together. So 20 times 30 is 600, and then I take the square root of 600. So the square root of 600 is about 24.49. So that's the geometric mean. It's not very hard, but you definitely need a calculator to do this part. So let's talk about how the Huntington-Hill method works. So first, you find the standard quota, the upper quota, and the lower quota using the same techniques that we've been using for this entire chapter. Then you find the geometric mean of the upper and lower quota. Then, if the standard quota is smaller than the geometric mean, you will give the state its lower quota. If the standard quota is larger than the geometric mean, you give the state its upper quota. And then step 4, if this apportions out the correct number of seats, we're done. Otherwise, we have to pick a different divisor, like we would do for Jefferson, Adams, and Webster, and start over and try again. So let's go through an example. I have 15 seats to apportion out, and I have 5 states. Here are their populations. So I need to find the standard quota, the lower quota, and the upper quota. We have done this over and over again, so I hope you'll forgive me if I go through this part fast. Standard quota of state A is 3.35, therefore the lower quota is 3 and the upper quota is 4. Standard quota for state B is 2.33, so the lower quota is 2 and the upper quota is 3. So for state C, standard quota is 2.8, so lower quota is 2, upper quota is 3. For state D, standard quota is 4.66, lower quota is 4, upper quota is 5. And for state E, my standard quota is 1.68, lower quota is 1, upper quota is 2. And if I find my totals, the standard quotas add to 15 like they're supposed to, the lower quota is 12, and the upper quota is 17. So now, if I want to do Huntington-Hill's method, we have all the information we need so we can start working on the apportionment. I'm going to take this slowly. It is somewhat complicated, so try and stay with me. We need to find the geometric mean for the lower quota and the upper quota for each state. And then, if the standard quota is lower than the geometric mean, we give the state its lower quota. If the standard quota is higher than the geometric mean, we give each state its upper quota. So I have a very complicated looking table here. I have the states, their population, the standard quota, the upper quota, the lower quota, not in that order, and then I have a column for the geometric mean, and the last column is for the apportionment. I could not fit the whole word apportionment in the box. So we're going to take this one state at a time, and I'm going to start with state A. So I have all the information for state A that I need, the standard quota, the lower quota, and the upper quota. So we need to compute the geometric mean of the lower quota and the upper quota. So 3 times 4 is 12, and then the square root of 12 is 3.46. So the geometric mean is 3.46. Now the standard quota is 3.35. So since 3.35 is smaller than 3.46, we are going to give the state its lower quota of 3. So I'm going to fill in the geometric mean and the apportionment on the chart for state A. So there it is. So now let's look at state B. Once again, I'm going to copy the relevant information over for state B, the standard quota, the lower quota, and the upper quota. The geometric mean is we take the lower quota times the upper quota, so 2 times 3 is 6, and then I take the square root of that, so the square root of 6 is 2.45. So the geometric mean, therefore, is 2.45. So the standard quota is 2.33, which is smaller than 2.45, so we're going to give state B its lower quota of 2. Note my typo. I'm too lazy to go edit it. So I filled in all the information for state B, the geometric mean, and the apportionment. So let's look at state C. So for state C, standard quota is 2.8, the lower quota is 2, the upper quota is 3. Geometric mean, 2 times 3 is still 6. Square root of 6 is still 2.45. 2.8 is larger than 2.5, so that means that we're going to give state C the upper quota of 3. So let's fill that information in the chart. And on to state D. So for state D, standard quota is 4.66, lower quota is 4, upper quota is 5. So the geometric mean, 4 times 5 is 20. Square root of 20 is 4.47. So the geometric mean is 4.47. And the standard quota is larger than the geometric mean, so we give state D its upper quota of 5. So I filled that information in the chart. And now on to state E. So for state E, the standard quota was 1.87, the lower quota is 1, the upper quota is 2. Geometric mean, 1 times 2 is 2, square root of 2 is 1.41, so the geometric mean is 1.41. So the standard quota for state E is larger than the geometric mean, so we will give state E its upper quota of 2. So I've got the apportionments there, so the only thing that remains now is to add them up, and I get my grand total of 15. So since I had 15 seats to apportion out, we are done. So I kind of rigged this to make sure that it did work on the first try, and I will continue to do that for you. However, in theory, if the total had not been 15, we would have had to go all the way back to the beginning, find a new standard divisor to get a new standard quota, and therefore a new lower quota and a new upper quota, find the geometric means of the new lower quota and upper quota, and hand the seats out and hope for the best. So this method has been used for quite a while, since the 1920s, and they haven't come up with a different one, so I guess this one has worked out pretty well.